Why, hello and welcome back to Lecture 8-1C, the final installment in our grid-based mapping lecture. So recall that from our summary and learning objectives, we know that an occupancy grid map is a popular approach for representing the environment of a mobile robot when you know the robot's poses in advance. In this approach, a cell is either occupied or free, and each cell is considered independent of each other. So they're each its own random variable, and it stores the posterior probability that the corresponding area in the environment is occupied. Occupancy grids can be learned efficiently by using a probabilistic approach, which is what we did in lectures A and B. And this lecture, we're going to focus more on reflection maps, which are an alternative representation to the grid-based map, where it stores each cell a probability that a beam is reflected back from that cell. And we use this to provide a sensor model by computing the likelihood of measurements and show that the counting procedure underlying reflection maps yields the optimal map. Please note that some of the slide content from these lectures comes from the website probabilisticrobotics.org and the text Probabilistic Robotics, written by Sebastian Thrun, Wolfram Burgod, and Dieter Fox. If you want to know more about their work, I highly encourage you to go visit their website. Let's go in. So first, let's recall from the previous lecture that we have a prior belief over every map that has a uniform distribution of 0.5. And then based upon, in this case, our sonar data, we then can come up with the probability that a cell is either occupied or free. And based upon that, we either mark it with a value less than 0.5 if it's free, or a value higher than 0.5 if it's occupied. So this represents the distance between the sensor and cell in consideration. And then at that certain value, if we're given a measurement Z, we can then determine whether it's occupied or free. An extension of this model would be for a laser. So for a laser, the model looks a little bit more binary because we say that for lasers, there's not much spatial resolution. So very similar, once again, we have the prior of 0.5, but now the probability of either occupied or free is not on the slope value, but it's either directly up or directly down, where we then would say, given that sensor value at that end minus R over 2 or plus R over 2, it either has a value or it doesn't have a value. So here is what the occupancy grid looks like for our laser scan, where now the laser is able to integrate over time, and the map does not necessarily have to be static because dynamic objects will go away as the laser continues to scan the environment. So here is what this looks like given this world after the laser scan. And this is an occupancy grid as well. And here's another example where we can compare the CAD map of the world to the occupancy grid made from the map by using this log odds approach that we've used earlier and described in lectures A and B. So now let's talk about how localization and mapping are related. Note that there is a strong dependency between localization and mapping because the probability of a given map cell value being occupied or free is based upon a sensor reading and the robot's pose at that certain time, or the probability of a given sensor reading at a certain value in time is based upon the cell value and the robot's pose. So you now can see that we can use Bayes' rule in order to relate these, where the probability of M given Z and X is equal to the probability of Z given M and X times the probability of M given X over the probability of Z given X. So now let's talk about an alternative to the occupancy or grid-based map model. And it's based upon a simple counting model where every cell you count. So if you send out a ping from a range sensor, then you would have hits X comma Y, which represents where a beam ended in terms of the cell location X comma Y, or misses X comma Y represent the number of cases where a beam passes through X comma Y. So then you would have the belief for the map cell X comma Y is the ratio of the number of hits over the number of hits plus the number of misses. And so the value of interest for us to do this calculation is the probability that a beam is reflected back from X comma Y in the world. And you can do this model with either laser or sonar. So the way the measurement model works is we know the robot's pose at a certain time, and beam in of scan T, which would be represented by ZTN, which is shown by this red line here. And then we would have a maximum range reading, delta Tn, which is equal to 1, or a beam reflected by back by an object is 0. So once again, beams reflecting things back, which shows 0 or occupied, or maximum range sensing would be a 1 or free. So on this graphic over here, red would represent our beam going from 0, 1 to N. And M is now the measured distance in number of cells. How many cells did that beam pass through before it reached the maximum range reading or it was reflected back? So the maximum range reading would then be ZTN minus 1, which are the cells covered by the beam. And that means that many would have to be free. So in this case, it would be N cells are free, looking at the diagram we have here. And so that would be the product from K equals 0 to ZTN minus 1 of 1 minus M f of X to Tn minus 1 if delta Tn is equal to 1. So that means if we got the maximum range reading, then all of those cells up to that point, we mark them as free. If we get delta Tn is equal to 0, that means the beam was reflected back. So you determine the measurement when that beam was reflected back, and you multiply that by the probability K equals 0 to KTN minus 1 is 1 minus that measurement. And that's how you find the likelihood of a measurement given the pose of the robot and the map. So computing the most likely map is you compute the values of M that maximize M star. So M star is the argument, and you want to maximize the probability of a certain map area giving the maximum beam reflection back, giving the sensor data and the robot's pose. So once again, we're going to assume we have a uniform prior belief for the probability of map, and this would be equivalent to maximizing the application of Bayes' rule. So M star would then be the probability of Z given X, M and X, and then you maximize the probability of a sensor reading at a given time T, given the map and the pose at that time T. This we can simplify once again because using our independence assumption that the sensor data at time T is independent and only depends on the pose at time T. Or in terms of our log odds, we can now take the log of that probability and change from a product to a sum, which is the log of the probability of giving that sensor reading at time T, given the map and the pose of the robot at time T. So what this looks like is M star would have the cell beams represented by these summations, n equal 1 to n, t equal 1 to t, j equal 1 to j. And then we have the log that the beam ends in cell j, given by this value here is equal to j, times 1 minus that maximum range times the log of that value being in cell j, plus the value that the beam traversed cell j instead of ended in cell j times the log of 1 minus the map value at that j. So we're supposing here that we can now represent certain terms as alpha j and beta j, where alpha j is the summation from t equal 1 to t, n equal 1 to n, of I of f of x n z, and that equals j, times 1 minus delta tn. And beta j is the summation of t equals 1 to t, n equals 1 to n, the summation from k equals 0 to z minus 1, I of f equals j. So what is the meaning of alpha j and beta j, which are extracted from that equation on the previous slide? We say that alpha j corresponds to the number of times a beam is not at maximum range and ends in a certain cell j, whereas beta j corresponds to the number of times a beam is intercepted at cell j without ending in it. So that means it misses that cell. So it's a matter of whether it hits or misses, and that represents alpha j and beta j. So when it's time to compute the most likely map, we want to maximize the function by finding the derivative and maximize for every j. So we can use the ray traces through the map from our sensors to find this model and find that it's consistent, but it's not require a lookup table like the previous model. You're just going to find the derivative. So now using that M star, you want to maximize the summation from J to J, where J represents the location of each cell, alpha J, the natural log of MJ, plus beta J, the natural log of 1 minus MJ, which represents the hits and the misses for each of the cell. And the way we do this is you take the partial derivative with respect to J of that map with respect to each cell, and you're going to have alpha J over MJ minus beta J over 1 minus MJ and set that equal to 0, because that's how we would then find the maximum value, where MJ is equal to alpha J over alpha J plus beta J. So computing the most likely map amounts to counting how often a cell has reflected a measurement and how often it was intercepted or traversed by a beam. So here's now an example of a reflection map. And what you should notice here is that this is the same map that we showed earlier for the occupancy grid. But there's one key difference between this one and the one before. Because there are glass panes at certain points in the map, if you're just looking at whether a cell is occupied or not, you may miss this when you're using just the occupancy grid approach. But by using the reflection map, you will get data reflected back from a glass pane that you may not get if you're looking at it to be occupied or not. So that's what this note is saying here, is that in an occupancy map, the locations of those glass panes would disappear. This map is consistent with the way it is done with localization, though, because you want to be able to use all of the data there, so you don't want to miss glass planes. So some of the key differences between an occupancy grid map and counting or the reflection map is that the counting model determines how often a cell reflects a beam. The occupancy model represents whether or not a cell is occupied by an object. And although a cell may be occupied by an object, the reflection probability of this object may be very small, such as glass. So here's an example. Out of 1,000 beams, only 60% are reflected from a cell and 40% intercepted without ending in it. So accordingly, the reflection probability would be 0.6. Now suppose the probability of an occupied cell given sensor data is 0.55 when a beam ends in a cell, and the probability of occupied given sensor data is 0.45 when a cell is intercepted by a beam, but it does not end in it. So accordingly, after end measurements, we will have the following calculation for the probability that a map is occupied. It would be 0.55 over 0.45 to the n times 0.6 times 0.45 over 0.55 times n times 0.4. So that would be 11 ninths to the n times 0.6 times 11 ninths to the negative n to the 0.4, or 11 ninths n times 0.2. Whereas the reflection map yields a value of 0.6, the occupancy grid value converges to a 1. And so finally, this concludes lecture 8-1C on using reflection maps and counting in order to represent a robot's world. Hopefully you can see the difference between this approach and the occupancy grid approach. Thank you for coming, and I hope you'll come back for the next 2 weeks of lectures, which is all about SLAM. Have a robotastic day.